I want you to take a second and just imagine the absolute most beautiful piece of jewelry you have ever seen in your entire life.
Oh, like sitting in one of those perfectly lit velvet display cases.
Exactly. Just picture it sitting there. Maybe it's a massive diamond ring or, a giant ruby necklace.
Like the classics.
Yeah, the classics. But when we look at traditional gems, like diamonds or rubies or sapphires, we are basically looking at the crystallization of the Earth's brute physical power.
Oh, absolutely.
Yeah.
I mean, to get a diamond, you need that crushing, just unimaginable pressure of the Earth's mantle.
Right? You need thousands of degrees of heat, and you need millions upon millions of years where it's just trapped underground in the dark.
It is geology at its most violent and extreme, really.
It is. But today, we are looking at a completely different kind of gemstone, like a gem that isn't forged by the crushing weight of the planet, but by life itself. Today, we are looking at the pearl.
It really is a profound contrast when you stop and think about the origins of the things we value. On one side of the jewelry store, you have stones born from volcanoes and tectonic collisions. And on the other side, you have the result of, well, biological quiet.
It's completely wild. I was going through the source material for today's deep dive, and it's this incredibly detailed article from a jewelry science series. It focuses on the biophysics and the nanotechnology of pearls. And, the mission for our deep dive today is to take all that dense, complex science and explain it based on the actual content so that it is super easy for the general public to understand.
Right, because it can get pretty technical.
Extremely technical, but we want to be perfectly faithful to the content, make sure there are no mistakes, but still make it a fascinating story for you listening. Because I just kept having these moments of sheer disbelief while reading this.
I don't blame you.
Because a diamond is, at the end of the day, it's really pretty raw.
Sure.
But a pearl is an actual biological miracle. You have this living creature, an Okoya oyster, just hanging out in the cold ocean water, minding its own business.
Eating its plankton.
Exactly, just eating plankton, and somehow it is manufacturing a flawless gemstone.
And doing it with a level of precision that human engineers struggle to replicate even in our most advanced laboratories.
Which is just crazy.
It is. But to truly appreciate what that oyster is doing down there, we have to start by dismantling a very common assumption about how a pearl actually looks.
Okay.
We need to deconstruct its most famous characteristic, which is that unique rainbow-like glow. In the jewelry world, that deep, iridescent shine is known as terry, or luster.
Okay, let's unpack this, because when I look at a really high-quality pearl, I see this incredible depth.
Right.
Like I see these subtle pinks and greens blending together, and they almost shift as I move the pearl around. Intuitively, you'd think there is some kind of pigment in there.
Like a dye or something.
Yeah, like the oyster is secreting a dye to color it. But the research is very clear on this. That breathtaking glow, that terry, is essentially an optical illusion.
Completely.
There is absolutely zero colored pigment inside a pearl.
None whatsoever. If you were to isolate the actual materials that make up the surface of the pearl, you would find that they are completely colorless and totally transparent.
Wow.
The color you are seeing is, well, it's an incredibly sophisticated trick of physics.
So if there's no pigment, it kind of reminds me of a soap bubble floating in the air.
Oh, that's a perfect analogy.
Because the soap itself isn't dyed pink or green, right? It's just clear soap and water. Or like the back of a CD.
Yes, exactly.
It's just clear plastic and aluminum, but when you tilt it in the light, you get that vivid, shimmering rainbow. Is the pearl doing the same thing?
You're touching on the exact mechanism there. Scientists call this phenomenon structural color, or light interference.
Light interference.
Right. To understand how it works in a pearl, you have to let go of the idea that light just bounces off the surface like a mirror. Because the outer layers of the pearl are transparent, the light actually penetrates deep into the gemstone.
Wait, hold on. I need to make sure I'm visualizing this correctly. You're saying light goes through a solid, rock-hard gem.
It does, yes.
How does light travel into a solid object without just stopping at the surface?
Well, it's because of how those layers are constructed. They aren't an opaque, solid mass. They are made of thousands of translucent microscopic layers.
Okay.
So when a beam of white light hits the pearl, a fraction of that light reflects off the very top layer. But the rest of the light beam passes right through that first transparent layer and hits a microscopic internal wall further down.
Oh.
And then again, a fraction reflects back, and the rest keeps traveling deeper to hit the next wall and the next.
Okay, so the light is penetrating, and at every single layer, a little bit of it is bouncing back out toward my eye.
Exactly. Now imagine all those returning light waves traveling back out from different depths inside the pearl.
Right.
Because they travel different distances, they're slightly out of sync with each other. As they emerge, these light waves literally crash into one another.
Like waves in the ocean.
Just like that.
Yeah.
If the crest of one wave lines up perfectly with the crest of another wave, they combine into a much bigger wave.
Yeah.
It's called constructive interference.
Okay.
And your eye perceives that supercharged wave as a very bright, highly specific color, like a vivid pink or deep green.
And what if the waves don't line up? Like if they hit each other off beat?
If the crest of one wave hits the valley of another wave, they cancel each other out completely.
Oh, wow.
Yeah, that's destructive interference. That specific color just disappears. So as you move the pearl, the angle of the light changes, the distances the waves travel change, and that complex microscopic dance of waves strengthening and canceling each other is what paints that shifting rainbow in your eyes.
That is fascinating. The light is literally colliding with itself to create color out of nowhere.
It is.
But that naturally leads to a huge biological question for me. If the light is bouncing off these internal translucent layers, what exactly are these microscopic walls made of? And how on earth is an oyster building them?
To answer that, we have to zoom way, way in. If you take a cross-section of a pearl and look at it under an electron microscope, like magnifying it tens of thousands of times, you don't just see a random chalky jumble of calcium.
Which is what you'd expect from a shell.
Right. But instead, you see a breathtakingly precise, highly organized structure that looks exactly like a brick wall. This microscopic architecture is called the pearl layer, or the nacre.
A microscopic brick wall. So we're talking about distinct individual building blocks here.
It is entirely architectural. And just like a brick wall you'd see on the side of a building, this nacre has two main components. You have the bricks and the mortar.
Okay, the bricks and the mortar.
The bricks are ultra-thin, completely transparent crystalline plates made of a mineral called calcium carbonate. Specifically, a very rigid crystalline form of it called aragonite. That is your structural foundation.
And the mortar. Because, I mean, if it's just a bunch of rigid crystals stacked on top of each other, wouldn't it just crumble?
That's the danger, yes.
Like chalk is calcium carbonate and chalk snaps if you look at it wrong?
Exactly. Which is why the mortar is so incredibly crucial. The mortar is a very special, sponge-like biological glue. The protein called conchiolin.
Conchiolin.
Yeah. The oyster secretes this protein specifically to stick those transparent mineral bricks together. Because the conchiolin is somewhat flexible, it acts like an organic shock absorber.
Oh, that makes sense.
It prevents the rigid aragonite crystals from shattering, which gives the pearl its incredible toughness.
Okay, so you have these transparent mineral bricks cushioned by this biological protein glue. But I was looking at the actual measurements of these bricks in the source text, and I need to run this by you because it seems almost impossible.
Let's hear it.
We aren't just talking about a few layers here. A pearl is made of thousands of layers stacked perfectly. And the text says a single one of these aragonite bricks is about 0.4 to 0.5 micrometers thick.
Yes. And just for context, 1 micrometer is 1,000th of a millimeter.
Wow.
So we are talking about structures that are entirely invisible to the naked eye.
Right, but here's the part that is blowing my mind. I was reading up on the properties of light to understand the interference you mentioned earlier. Human visible light, like the actual spectrum of light waves that our eyes can detect, has a wavelength that falls roughly between 1.4 and 0.7 micrometers. Is it just a massive coincidence that the oyster's bricks are 0.4 micrometers thick, which perfectly matches the wavelength of human visible light?
It's not a coincidence at all, though it is one of the most stunning marvels of evolutionary biology. You've hit on the exact reason why the pearl's luster exists in the first place.
Okay.
For light interference to work effectively and produce vibrant colors, the thickness of the layers the light is passing through must be on the exact same scale as the wavelength of the light itself.
That is staggering. Like the oyster has no concept of physics.
No, of course not.
It doesn't have a degree in optics. It doesn't even have eyes like ours to appreciate the rainbow it's making. Yet, purely through the blind trial and error of evolution, it is manufacturing nanobricks that precisely match the dimensions required to manipulate the wavelength of visible light.
It is an accidental masterpiece of engineering.
Totally.
The oyster is really just trying to create a smooth, defensive barrier to protect its soft tissue from an irritant, like a parasite or some debris. But in doing so, it just stumbles into the perfect optical physics.
But how does it physically do it? Because if human engineers want to build something on the nanoscale, if we want to manipulate matter at the level of a single micrometer, we need sterile, clean rooms.
Oh, yeah.
We need giant vacuum chambers, computer-controlled lasers, and millions of dollars of equipment. Or, going back to our diamond analogy, if we want to synthesize a diamond, we have to replicate the Earth's violent power. We need machines that generate tens of thousands of atmospheres of pressure and blast furnaces heating carbon to like 1,500 degrees Celsius. It's a massive, energy-hogging, incredibly aggressive process.
We actually call that the heat, beat, and treat method of human manufacturing.
Heat, beat, and treat.
Yeah, we use brute force to bend materials to our will.
Exactly. And then you have the Akoya oyster. It's just sitting in cold ocean water. It's casually filtering plankton. It's not stressed out. It's not using massive amounts of heat. And yet it is building flawless, perfectly measured nanotechnology at room temperature and normal atmospheric pressure.
Unbelievable.
It completely defies everything human manufacturing requires.
It's a phenomenal contrast. What's fascinating here is a phenomenon known as biomineralization.
Biomineralization.
Yes, it's the process by which living organic organisms create inorganic minerals. And how the oyster achieves this without a 1,500-degree furnace is just a masterclass in biological chemistry. It isn't using heat. It's using chemical self-assembly, directed by a highly coordinated molecular-level tag team of proteins.
Okay, walk me through this tag team. How do proteins build a microscopic brick wall?
Think of it almost like a biological 3D printer that constantly turns on and off.
Okay.
The oyster's mantle tissue secretes calcium and carbonate ions into the space where the pearl is forming. But those ions won't just stack themselves into perfect bricks randomly. So the oyster secretes a very specific protein that acts like a construction foreman.
A microscopic form.
Exactly.
Yeah.
This first protein sets down a chemical template, a nucleation site, that essentially signals, hey, plant a crystal seed right here.
So it creates a sticky spot for the calcium to attach to.
Precisely. Once that template is down, the calcium and carbonate ions in the seawater naturally bind to it, and the aragonite crystal begins to grow. It starts building the brick.
But if it just kept growing, the brick would get too thick, right? It would grow past that 0.4 micrometers, the light wouldn't interfere correctly, and you wouldn't get the rainbow.
That's exactly the danger, and that is where the second protein comes in. As the crystal reaches that perfect 0.4 to 0.5 micrometer thickness, the oyster releases a different protein.
Okay.
This second protein physically binds to the top, growing face of the aragonite crystal. By attaching itself to the surface, it blocks any more calcium ions from attaching. It chemically caps the brick and says, stop, don't let this crystal get any thicker.
Wow. So it's a constant, incredibly precise chemical stop-and-go communication at the molecular level. Start the crystal, stop the crystal, lay down the conculin mortar, start the next crystal.
Exactly. This highly coordinated back-and-forth process is called layer commitment.
Layer commitment.
Yes, it guarantees that every single brick is uniform, layer after layer, for thousands of layers. And when you understand the sheer elegance of that mechanism, you begin to see why modern material scientists are absolutely obsessed with the oyster.
Because they want to steal its blueprints.
Oh, without a doubt, there is an entire rapidly growing field of science dedicated to this called biomimetics, which literally means imitating nature.
Yeah.
Think about the implications here. Our human manufacturing, as we discussed, is loud, hot, and wasteful. But if we can truly master the oyster's technique of layer commitment,
If we can copy the proteins.
right, if we can figure out how to program proteins to direct the self-assembly of inorganic structures at room temperature, it would fundamentally revolutionize human technology.
What kind of things could we build if we figured that out?
Well, imagine building ultra-lightweight, shatterproof armor inspired by that shock-absorbing nacre structure.
Like biological Kevlar.
Exactly like that. Or imagine manufacturing completely flawless, scratch-resistant optical lenses for telescopes or cameras without ever turning on a furnace. We could build structural components for aerospace engineering using a fraction of the energy we currently use, with virtually zero carbon emissions.
It's like the ultimate green technology, and it's just been sitting at the bottom of the ocean this whole time. The oyster is out-engineering our top scientists while eating plankton.
It really is.
But I want to pivot for a second. Knowing all of this microscopic architecture, knowing about the proteins and the layer commitment, how does this actually help me if I'm standing at a jewelry counter trying to buy a pearl? Does this biophysics translate into actual consumer advice?
Oh, it translates perfectly. The quality of a pearl you see in a shop, its value, its beauty, is entirely dictated by whether or not that microscopic structure formed correctly.
Okay.
According to the research, a top-tier, highest quality pearl has to meet two very strict scientific conditions.
Let's hear it. What's condition number one?
The first condition is uniform brick thickness. As we talked about, for that terrier luster to be perfect, the light interference has to align flawlessly.
Right, the waves have to crash perfectly.
Exactly. That constructive and destructive interference only happens if every single layer of aragonite is exactly the same thickness.
Right.
When an oyster is in peak health, its metabolism is stable. That protein tag team works smoothly, the stop-and-go signals are perfectly timed, and the layers are identical.
Giving you the rainbow.
Right. The light waves bounce back in perfect harmony, giving you that vibrant, shifting rainbow.
So if uniform thickness guarantees that beautiful rainbow color, what happens if the oyster isn't perfectly healthy? Let's say there's a really harsh winter, the ocean gets too cold, or there's an algal bloom that stresses the oyster out.
That is when the manufacturing process breaks down. If the oyster's health declines, its metabolism fluctuates. Those formin proteins lose their rhythm, and the layer commitment fails.
Oh no.
Yeah. As a result, the thickness of the bricks becomes irregular and sloppy. One layer might be 0.4 micrometers, the next one might be 0.8, the next one might be jagged.
And I'm guessing light does not like jagged, irregular walls.
Does not.
Hmm.
When light penetrates an irregular wall like that, the waves don't interfere in a structured, rhythmic way. They just scatter randomly in 100 different directions.
Yeah.
In optics, this is called diffuse reflection.
Diffuse reflection. And what does that actually look like to the naked eye when you are looking at the pearl?
It looks dead. Yeah, instead of a deep, iridescent rainbow, you just see a muddy, flat white bead. It might be perfectly round, it might technically be a pearl, but it has no luster, it has no life to it.
So a muddy white pearl is basically a physical record of a stressed out oyster.
Basically, yes.
Okay, so uniform thickness is condition number one. What is the second condition for a really top tier pearl?
The second condition is a very high number of total layers. Jewelry experts refer to this as having good makey.
Makey.
Yeah, which translates roughly to the thickness of the nacre as a whole.
So if uniform thickness gives you the rainbow color, what does having good makey, or thousands of layers, actually do for the look of the pearl? Because some of them look like you can just stare a mile into them.
That's exactly what good makey provides, its depth. If a pearl is cultivated slowly and wrapped in thousands upon thousands of thin uniform layers over a period of several years, there is simply more physical material for the light to travel through. The light penetrates deeper and deeper, bouncing back from much further inside the core of the pearl. This creates a visual effect where the glow doesn't just look like a shiny glare painted on the surface. It looks like a rich, three-dimensional light that is literally welling up from the bottom of the gem.
It gives it that inner fire. I was thinking about this when reading the source material. If a pearl's luster relies on years of perfect uniform layers, then a pearl isn't just a gemstone, it's essentially a historical health record.
Yes, an environmental core sample, if you will.
Exactly, a core sample of that specific oyster's life. A bad winter, a week of pollution, a sudden spike in ocean temperature, all of it is recorded as a bad brick in that specific layer.
That's entirely accurate.
If you see a pearl with a dull spot, you are seeing a week where that oyster was struggling. But when you look at a flawless pearl with perfect luster and incredible depth, you are looking at years of perfect health, a stable environment, and the sheer biological diligence of that oyster working day after day. You aren't just buying a pretty accessory, you're buying a biological diary.
It completely reframes the entire experience of looking at jewelry. You stop seeing a static object and start seeing a chronological process.
It really does. It changes everything. So let's take a step back and summarize this journey we've been on today. We started this deep dive just looking at a shiny, pretty object in a velvet case. But by peeling back the layers, literally and figuratively, we uncovered an elegant, perfectly efficient nanotechnology factory operating silently inside a simple mollusk.
A factory that, frankly puts our most advanced laboratories to shame.
It really does, and it brings me right back to that contrast we started with. We culturally think of diamonds as the ultimate gemstone, and they are incredible. But diamonds are the crystallization of the Earth's overwhelming physical power.
They are heat and violence and crushing pressure.
Right. Pearls, on the other hand, are the crystallization of an overwhelming microscopic order. They are spun into existence by life itself, perfectly matching the physics of visible light at room temperature just to survive.
And that leaves us with a rather profound thought to consider.
Let's hear it.
We've spent this entire time marveling at an oyster. A simple, unassuming creature that has spent hundreds of millions of years quietly perfecting zero energy, room temperature nanotechnology at the bottom of the sea, armed with nothing but seawater and a few proteins. It forces you to wonder, what other miraculous world-changing manufacturing secrets are hiding in plain sight right now? What other incredible engineering blueprints are locked away within the biology of the natural world, just waiting for human science to finally catch up and notice?
That is exactly the right question to be asking. Thank you so much for joining us on this deep dive into the biophysics and the incredible hidden world of pearls. We hope we've shed a little bit of light on the magic happening beneath the waves, and we hope you never look at nature or that jewelry case the same way again. Keep wondering, keep exploring, and we will catch you on the next deep dive.